Yeah, last week we started with organic chemistry and we spoke generally about organic compounds and the millions that are out there. And we spoke about what are hydrocarbons. Let us see. We spoke about hydrocarbons, which are compounds, organic compounds that are made only out of hydrogen and carbon. And, and why did we start with the hydrocarbons? And especially the alkanes, because these are actually the alkanes form the basis on which we name any other organic compound of any complexity. So what we need to remember about this naming, referring to the alkanes, straight chain alkanes, was that if the molecule has just one carbon, the prefix of the name is the meth, so this is called methane. If it has two carbon, it's eth, so this would be an ethane. With three carbons, propane, butane, and so on. We said that the first four, we should learn their names by heart. And the others, pentane, hexane, heptane, and so on, we're going to meet them occasionally, but I think you get the idea of how their names come from. Okay, so considering that we have, with the name of the alkane, which is given in this column, they also give us here two types of representing this molecule. And here you see this column is called structure, whereas this column is called molecular formula. It's actually the molecular formula of the compound methane. And this would be the molecular formula of the compound ethane, and so on, molecular formula. So it becomes obvious that there are different ways to represent organic compounds. In fact, I think did we say last week that the molecular formula, strictly speaking, is not so extremely helpful in organic chemistry because we can't really see the structure of the molecule and the type of bonds that are there. So we prefer other types of formulas. So let us see three main types of formulae for organic compounds, which will be very useful for us. But they're not only three, there are more than three. For example, here in this part, there are all sorts of different types to represent a compound, but we're not going to talk about all of them now. So let us begin today's lesson with these types of formulae that I want us to know for starters at least. So the three types of organic formula we are going to discuss here. The one is the molecular formula, which we spoke about already, then the structural formula, and then the displayed formula. So these two formulas, we are going to meet them very often. And in fact, we're going to use them the most often from all, because these formulas give us an idea of how the molecule looks like. It helps us to understand how it will behave and how to name it, of course. Now, let us take a simple example to apply in these formulas. Like, let's take ethane that has two carbons. And of course, each carbon will, the remaining bonds will be bonded with hydrogen, since it's an alkane and it's a hydrocarbon. The rest will be hydrogens, of course. So these bonds are bonding the carbon with hydrogens. So this would be the hydrogen, a molecule of ethane. Okay. This prefix is the characteristic of two carbons when we have two carbons in our chain. Now, the molecular formula of ethane would be, the molecular formula just shows how many atoms of each type there are in the molecule. So we have carbons, we have two carbons, so carbon 2, and then we also have hydrogens, lots of them. How many? We have 2, 4, 6, isn't it? So this would be the molecular formula that simply shows how many atoms of carbon there are in the molecule and how many atoms of hydrogen without telling us anything, any other information. Now the structural formula now, it's more revealing. How do we make the structural formula? In the structural formula, we split the carbons. We split the atoms not the atoms, the carbons that exist in our molecule. So here we have two carbons. So we separate the carbons, and next to each carbon, we show what else is this particular carbon connected to, bonded to. For example, if we talk about the first carbon, we also see another 3 hydrogens there. So we put its hydrogens next to the carbon, and this is the one lot, the one part of the carbon, the one carbon of the molecule. The other carbon, will do the same for the other carbon. We write it next to the first lot. So the second carbon again is there, and it's linked, it's bonded to another 3 hydrogens. So this type of formula that shows each carbon and what it's connected separately, it's called a structural formula. So this is structural formula. Sometimes you're going to see the structural formula with like that, for example. We might see it in some books in this form. That's also structural formula. It's the same thing. But usually, I mean, strictly speaking, we are not supposed to show bonds. We just show the carbon atoms split from one another in the chain, and together with whatever else they are connected to. Because remember, each carbon can form 4 bonds. So one bond is there with the other carbon, but the other 3 bonds must be bonded to something else, isn't it? Because this is a hydrocarbon, they are bonded to hydrogens. So there's the structural formula. Then the next thing is the displayed formula, which is actually what I drew there. The displayed formula, it's actually the easiest way to represent an organic compound, because we can see everything there we can see how the carbons are connected, what else is connected to the carbons, what type of bonds there are between carbon atoms or carbon and something else. And so the displayed formula, it's actually the formula that shows us everything. And it's a pain really to draw it, especially if it's a long hydrocarbon chain, but it pays, especially if we are beginners and we want to understand what's going on and where things are. It's the best formula to help us. It's also the best formula to help us name the various compounds, and especially the more complex they are, the easier for us will be to draw the displayed formula to know where things are and number the carbons and so on. Okay, so these are the 3 important types of formulae that we need to know for now and for our level especially. So the molecular, the structural, and the displayed. We also need to remember these names again. You see, in organic chemistry, we need to have a good memory. We need to remember things, quite a few words. So these are the 3 names of the formula: molecular, structural, and displayed. And very often in exam questions, for example, they might ask us to draw the display formula or draw the structural formula or find the structure and this and that. So we need to know what they're referring to by remembering those names. What is the structural formula and what is the displayed formula? All right. So another thing that we need to talk about now, because we talk a lot about alkanes up to now, alkanes. The alkanes are this type of hydrocarbons that have all single bonds. This is it's a family of organic compounds which we call alkanes. This whole family, a family of compounds that behave in a very similar way, and have very similar properties, are called homologous series in organic chemistry. So alkanes is one type of homologous series. homologous series. So alkanes is one type of homologous series in organic chemistry. So let us discuss about another three more homologous series, just to know their names and roughly how they look like. So in general, homologous series are families of organic compounds with similar properties. Okay. Let's just, I have not brought pictures here, but we can draw them by hand. Organic groups of compounds are called homologous series, like the alkanes, and here we have them on top to remind us that this is a part of the one important type of homologous series. And let us follow again with the example of the ethane and see out of the ethane how we're going to write other homologous series with two carbons in the chain. Okay, so let us begin with this one, because this is the ethane. Okay, so this is already an alkane. It's part of the alkanes. Ethane is part of the alkanes with two carbons. So here is our example of an alkane, the ethane. Another example would be the propane. Propane has three carbons in its chain. The rest of the bonds obviously are hydrogens, okay? Hydrogen, all of them. So this is the top is the ethane, the bottom is the propane, and we could write an alkane with any type and any number of carbons in a chain. Okay, so this is the ethane, this is the propane, both alkanes. Now, another very important homologous series in organic chemistry is the alkenes. Look at this, how similar it is, alkenes, and this is alkanes. Be careful, it's a very, very different type of hydrocarbon, the alkenes, because these are unsaturated, they have a double bond. So what would be the alkene that corresponds to ethane? It would be the ethene. And how could we draw the ethene? Would be one with two carbons, because it's an ethene, but it has a double bond between the two carbons are bonded together with a double bond. Now, remember that each carbon atom can form 4 bonds, okay? So for each carbon atom, in other words, needs another 2 items to bond with, which will be hydrogens in this case, because alkenes are also hydrocarbons. So you see now each carbon atom has 4 bonds, like 1, 2, 3, 4. Double bond, of course, counts for 2. And the other carbon on the right, 2 bonds here, and another 2, 4 altogether. So this is how we show an alkene. In our case, this is the ethene. An example of an ethene. If we had a propene, again we would have one single bond somewhere, and but we would have 3 carbons in the chain. So the double bond could be either here or there. Let's place it here. It doesn't matter. In both cases, would be a propene. But now let us see how many hydrogens we must add here. The first carbon needs another 2, another 2 hydrogens. The carbon in the middle has 1, 2, 3 bonds and needs another hydrogen. Let's place it up there. And the carbon on the right-hand side needs another 3 to make its 4 bonds. So this is how it could look like, okay? Note that I could also make a propene with a double bond there, but it would really be the same, isn't it? So this could be, it's another type of alkene, which is the propene. you see the ending of the words of the names is the same ending as the name of the homologous series, propene, I think. Now, let's another two important homologous series are the alcohols and the carboxylic acids. These are actually the acids that we find in organic chemistry, which correspond to the acids that we find in inorganic chemistry. But usually the organic chemistry acids are weak acids. They're not as strong as the ones we find in inorganic chemistry. Anyway, now let's the alcohols now. An alcohol is it's another homologous series that has a hydroxide. The hydroxide ion is this, but let us show it in a proper molecule, organic molecule, again with two carbons. So a molecule of an alcohol that corresponds to ethane would have two carbons in a row, and one of the hydrogens in the molecule would be connected with this hydroxy group instead of a hydrogen. So all the others will be hydrogens. So this is how an alcohol looks like. Okay, so this is the characteristic of an alcohol. In organic chemistry, this is called the hydroxy group or a hydroxyl, but we'll talk a bit more about that. It's not necessary to say everything now. So this is how an alcohol would look like. And this would be an ethanol. The ending of the word in the ending of the name of alcohols is, what am I writing there? Sorry, let me concentrate. Ends in ol. So ethanol. So the root is the same, since we have two carbons, but the ending is ol. It's a characteristic of the alcohols. They end in ol, the names. All right. And if we had from the root, if the root was propane, our alcohol would be propanol, and it would have 3 carbon atoms in it, the chain, and one of the hydrogens would be replaced with this hydroxy group again. Let's place it here. It can be placed in other places as well, but let us keep it now there for simplicity. And that would be another alcohol again. In this time, it is called propanol. Comes from propane, propanol. The ending, ol. The carboxylic acids again will have the same basic root, but the ending now will be different. Now, let me write down. Draw a carboxylic acid first, and then we'll explain what's going on. Now, the carboxylic acid, one of the carbons is connected to one oxygen and one hydroxy group again, and the others will have hydrogens. So this part here is the characteristic of the carboxylic acid. All the carboxylic acids in organic chemistry will have this carbon connected to this oxygen and this hydroxy group. So all this lot here, this complex kind of group of atoms, is characteristic of the carboxylic acids. Now, to name it again, it has 2 carbons, therefore its root name will stem from the from ethane, but now we call it ethanoic acid. So all the acids, the organic group acids, end in oic acid, and the word acid afterwards. So the root is from ethane, we can see that, but the last E has been replaced with oic, oic acid, and we must not forget to say acid as well, of course. So there it is. And if we were to show the propanoic acid, I would simply have to have 3 carbons. By the way, one of the 3 carbons is the carbon that is connected with, is part of all this lot that is the characteristic of the acid. It doesn't matter. This carbon is part of the name. As far as we are concerned, this has a chain of 3 carbons. So this will be propanoic acid, and here is its characteristic group here, and the rest will be hydrogens. In the ethanoic acid, this complicated lot at the end is always at the end, whereas in the alcohols, this hydroxy group here can be in any other position, even in the middle of the molecule. But in the ethanoic, in acids, this characteristic lot here, which we call characteristic group, has to be at the end. So these are the 4 very important homologous series that we are going to meet in our level. And of course, we need again to remember our names: the alkenes, the carboxylic acids, the alcohols, and the alkanes. The alkanes and the alkenes are hydrocarbons, as you can see, but the alcohols and the carboxylic acids are not hydrocarbons because they also have oxygen. Oxygen is not part of hydrocarbons. Eh? So we see that all the family in each homologous series has something common. What is the common thing that all its members have? It's these groups of atoms that characterize the series, the family. All this group here, which is the characteristic of the carboxylic acids, or the hydroxy group here, which is the characteristic of all the alcohols. And what is the characteristic of the alkenes? It's the double bond. All the alkenes must have a double bond, or perhaps more than one. But they must have at least one double bond. This would be the alkenes. So this characteristic that determines not just the name of the group, but the chemical and physical properties, we call it a group. So we call it a functional group, not just a group, sorry. Okay, I would like, let's make the page a little bit smaller. All right, so each homologous series shares some common characteristics. Actually, the important characteristic that it shares is the functional group. They have the same functional group. And when we say functional group, it's such a funny name, but don't be confused. The functional group could be a double bond, could be a triple bond, could be one atom, like, I don't know, some halide, some chlorine, for example, that has replaced a hydrogen. It could be the hydroxy group that we have here, could be this hydroxy group, or it could have been this group that we meet in the carboxylic acid. So any of these items that is there in the molecule and it characterizes the series, we call it the functional group because it determines the properties of the molecules of this homologous series, of this particular homologous series. Maybe, you know, well, there are two more characteristics of each homologous series. Let's discuss it quickly, and I hope we'll have time. Members of the same homologous series also show gradual change in their physical properties, which means, actually, before we explain that, let us go to the third point to finish with the points. The third point is that members of the same homologous group have a common formula. They have the same general formula. The same general formula. Let's talk about the formula first, which is the easiest, before we discuss what does it mean gradual change in physical properties. Now, the same general formula. If you look at all these alkanes, say this ethane has 2 carbons and 6 hydrogen connected. Its general formula, the general formula of the alkanes is carbon N and hydrogens 2N plus 1. All of the alkanes will have the same general formula, where N is the number of carbons. Here in the case of the ethane, we have 2 carbons, so N is 2. Then the hydrogens are 2 times 2 plus 1. Sorry, not plus 1, goodness, plus 2. My goodness, plus 2. So altogether, in other words, if you look at, we have 6 hydrogens, isn't it? So N, for N equals 2, it's, this would be 4 plus 2 equals 6. So N, remember, is the number of carbons in the molecule. All of the alkanes will have the same general formula. For propane, N equals 3. So how many hydrogens are there? 2 times 3 is 6, plus 2, 8. So all the hydrogens of the propane are 8. In the alkenes now, it has less hydrogens because of the double bond. So what is the general formula for alkenes? Is carbon N and hydrogens 2N. And again, you can see, if you replace the N with a number of carbons here, you are going to see that indeed it applies to all of the members. In alcohols, what would be the general formula? It would be similar to that, but one hydrogen has been replaced by a hydroxy. So its general formula would be carbon N, and hydrogens would be 2N plus 1, and the rest would be the what is this? The hydroxy. So you see, instead, one of the hydrogens has been replaced with a hydroxy group, isn't it? So this is the general formula for the alcohols. And then for the carboxylic acids, where can I write for the carboxylic acids? Let's write it down here. Again, N carbons, and hydrogens now will be 2N plus 1 again, but the 1 would have been replaced by all this group here, this characteristic group of the carboxylic acids. Here it is. So every single homologous series has the same general formula. As far as the gradual change in physical properties now are concerned, means, for example, if we take a physical property, like a very important physical property is the melting point or the boiling point. If we were to plot, if we make a graph of the boiling point against the number of carbons in the chain, we are going to find a line which is nearly straight line that goes up gradually, as we can see, as the number of carbons in the chain increases. So we see, for example, in this example, the top, the green here corresponds to carboxylic acids. All carboxylic acids, look at this. This would be one carboxylic acid with just one carbon, methanoic acid, in other words, would have this boiling point at about, what is this, 100 degrees, I suppose this is degrees Celsius. If we have another acid with 2 carbons, ethanoic acid, its boiling point goes a bit higher. With 3 carbons, a bit higher. With 4 carbons, higher. Gradually, it increases, but in a smooth kind of way. It's not in a sudden or random or haphazard way. So this is what it means, gradually. What is the red line corresponds to alcohols. Again, the same applies to alcohols. You see how the boiling point increases as the number of carbons increases, and so on. But the yellows are for the alkane and the gray for the alkenes as well, very similar lines. This is what means gradually, nothing radical and out of the ordinary. But now we have to stop here. And I hope this made some sense. Just to remind ourselves next week that we have this, we spoke about these 4 homologous series, and we just need to know the characteristic, the functional group, in other words, okay? So slowly we'll get there. Okay, guys, hope you keep well, and I'll see you tomorrow or next week. We'll see. Okay, bye.